One of the most common problems observed in masonry chimneys, and masonry in general, is spalling brick, where the face of the brick flakes, chips, or breaks apart. Many homeowners believe this is caused by poor quality brick or environmental exposure, but the root cause almost always traces back to the original construction. The International Residential Code establishes strict requirements for masonry joint dimensions, particularly in Section R606, 3.1, which governs the thickness of bed joints, head joints, and collar joints. These joints must be constructed to uniform thickness using the correct mortar type to ensure that the brickwork behaves as a unified system. Mortar selection is critical. Mortar must be softer or lower in compressive strength than the brick units themselves. Mortar is engineered to act as the sacrificial component of the wall, deforming and crushing slightly under movement, moisture expansion, and thermal cycling to protect the harder brick units. Historically, this was well understood, and masons used type-in mortar for chimney construction because it is more flexible and has a lower compressive strength appropriate for most brick. However, many modern masons routinely use Type S mortar, which is significantly stronger and harder. When a high-strength mortar is paired with standard or softer brick, the mortar can no longer accommodate the natural expansion of the brick. The mechanism of spalling is straightforward. Brick is a porous, absorbent material that naturally expands as it takes in moisture. When expansion occurs, either the mortar joint yields or the brick does. If the mortar is too hard, the stress is transferred into the brick, causing the face of the brick to crack and eventually flake away. Over time, repeated wetting, freezing, and heating cycles accelerate the damage until the brick visibly spalls. In other words, spalling is not a failure of the brick. It is a failure of the mortar selection and joint construction. Proper chimney construction begins with adequate wall thickness, compliant joint dimensions as specified in IRCR 606, 3.1, and the correct mortar type suited to the compressive strength of the brick. When these elements are properly executed, the chimney becomes a durable, resilient structure capable of withstanding weather, heat, and time without deterioration. Failure to follow these basic principles, however, inevitably leads to premature brick damage, leaking, thermal transfer issues, and costly repairs. Efflorescence is the white, powdery, crystalline substance that often appears on the surface of masonry chimneys. It forms when water dissolves natural salts within the brick or mortar, then carries those salts to the exterior surface where the moisture evaporates and leaves the crystals behind. While many people assume efflorescence is merely cosmetic, it is actually a clear indication that moisture is moving through the chimney. That moisture can come from two different directions, either from the outside penetrating inward or from inside the chimney pushing outward. When water enters from the outside, it typically comes through defects such as a cracked crown, missing or improperly installed flashing, porous brick, deteriorated mortar joints, or a missing chimney cap. Once inside the masonry, the water travels outward by capillary action and brings salts to the surface. The appropriate solution for this type of efflorescence is to stop the water from entering the masonry. Structural defects must be repaired first. This may include crown reconstruction, flashing correction, tuck pointing, or replacing damaged brick. After the masonry is structurally sound, the chimney can be treated with a breathable masonry water repellent. Professional-grade repellents allow vapor to escape from the masonry while blocking liquid water from penetrating the surface, keeping the chimney drier and preventing future efflorescence. Moisture, however, can also form from inside the chimney, especially when gas appliances vent into a masonry flue. Gas combustion naturally produces water vapor. In a large, cold masonry chimney, these flue gases cool too rapidly. As the temperature drops, the vapor condenses on the interior walls of the flue, saturating the masonry from the inside out. This internal condensation dissolves salts in the brick and mortar just as exterior water does, and eventually the salts migrate outward and appear on the exterior surface. Moisture created by gas appliances is particularly aggressive because it is acidic and can deteriorate mortar joints and clay flue tiles quickly. One of the most effective solutions in this situation is the installation of a properly sized stainless steel liner. A stainless steel liner keeps the flue gases warmer and prevents condensation from forming. It also confines the moisture within the liner system, reducing the amount of water that can enter the masonry itself. In summary, efflorescence occurs because moisture is either entering the chimney from outside or forming inside from gas appliance condensation. by addressing both potential sources, repairing exterior water entry points, and protecting the flue with a stainless steel liner when necessary. Efflorescence can be eliminated, and the masonry chimney can be protected from long-term damage. Chimney shoulders are the outward sloping sections of a masonry chimney that form where the chimney transitions from a wider base inside the house to a narrower stack above the roofline. They are, in effect, the exterior counterpart to the smoke chamber located inside the chimney, which tapers inward toward the flue. While the smoke chamber narrows as it rises, the chimney shoulders widen as they ascend, creating the opposite shape on the outside of the structure. Chimney shoulders are necessary whenever the chimney footprint at the base is larger than the portion that extends above the roof. This often occurs when the chimney sits on an interior wall or spans multiple floors with fireplaces or flues that require additional space. To transition from the wider section to the narrower upper chimney, masons build step projections called corbels, which create the slope profile commonly seen in chimney shoulders. Because chimney shoulders form flat or sloped surfaces that are exposed to the weather, they must be carefully constructed to shed water. Some chimneys use a gentle masonry slope so water runs away from the chimney body. Others use a concrete cap or a parged coat of mortar applied over the corbels to smooth out joints and create a watertight surface. In many cases, masons apply a fully paved masonry surface, sometimes referred to as parging or paving over, to eliminate ledges, cracks, and brick voids where water could collect. The goal is always to provide a continuous, water-shedding plane to prevent moisture infiltration. Chimney shoulders should never be corbelled out too aggressively. Standard bricks contain hollow cores or brick holes, and when corbelling is extended too far, those cavities become exposed or minimally covered. These voids trap and hold water, especially if the shoulder is not properly parged or capped. Once water enters these brick holes, freeze-thaw cycles, efflorescence, and internal saturation can cause rapid deterioration of the chimney. Excessive corbelling can also make the shoulders structurally weak, putting stress on the lower sections of the chimney. Properly built chimney shoulders should rise in small, controlled steps that maintain brick stability and allow for a smooth and protected exterior surface. They must be capped, sloped, parged, or otherwise finished to shed water effectively. When constructed correctly, chimney shoulders form a durable transition between the wider chimney base and the upper stack. When built improperly, they become one of the most common areas for water intrusion, masonry decay, and structural damage in the entire chimney system. An exterior chimney constructed as a buck chimney is one of the most vulnerable chimney configurations because it is not structurally tied into the house. A buck chimney is essentially a freestanding masonry column that happens to sit beside the home. The chimney has its own foundation, its own mast, and its own movement, while the house has a separate foundation and moves independently. Because the two structures behave differently under loads such as wind, thermal expansion, soil settlement, and frost heave, the chimney often begins to separate from the house wall over time. This separation is one of the most common structural failures seen in older masonry chimneys. Small gaps form between the siding and the chimney. Mortar cracks appear along the house-facing side. The chimney may begin to lean outward, or the entire structure may settle lower than the home's foundation. All of this happens because the chimney is not integrated into the framing. Essentially, the house and chimney are two independent systems standing inches apart rather than one unified structure. If one intends to build a chimney so that it sits directly beside and in contact with the home's structural framing, the proper method is to ensure that the masonry wall touching the timber is at least 12 inches thick. This requirement provides adequate fire resistance so that wood framing may safely abut the chimney. A traditional 4-inch or even 8-inch chimney wall is not thick enough where it intersects with combustible framing because heat transfer over time can raise the temperature of the wood to unsafe levels. 12 inches of solid masonry creates the required heat barrier and allows the framing to meet the masonry without violating clearance to combustible requirements. In addition to increasing the masonry thickness at the house interface, brick ties or masonry anchors can be installed to mechanically connect the chimney to the home's framing or sheathing. These ties help prevent the chimney from drifting away as the two structures experience differing movement. Properly installed masonry ties limit outward rotation, reduce separation at the siding line, and keep the system functioning as a single, stable unit. By building a thicker chimney wall where the structure meets the home and tying the masonry to the framing, the chimney is no longer a true buck chimney. Instead, it becomes a partially integrated system, far less likely to lean, crack, or separate over decades. These construction methods produce a chimney that is safer, more stable, and better able to withstand weather, settlement, and wind loads. A vertical crack in the brick and mortar joint on the outside of a smoke chamber is one of the most commonly misdiagnosed chimney defects. Many technicians and engineers automatically assume these cracks are caused by foundation settlement, but this conclusion is usually incorrect, especially when all the mortar joints remain straight and level. Level joints indicate that no downward movement has occurred. Instead, these cracks almost always result from thermal stress, and the root cause is improper construction inside the smoke chamber area. The International Residential Code is very clear on smoke chamber wall requirements. IRCR 1001.8 requires the front, back, and side walls of a smoke chamber and fireplace to be at least 8 inches thick, unless the chimney uses a listed liner system that provides equivalent protection. Despite this, many chimneys are improperly built with only 4-inch thick walls. This reduced thickness significantly increases heat transfer because it provides only half the mass needed to buffer and distribute internal heat. At the same time, the code also requires the interior surfaces of the smoke chamber to be parged smooth with refractory mortar. This refractory parging does two important things. First, it smooths the interior surfaces, improving draft and reducing turbulence. Second, and more important for this discussion, it acts as a thin but effective insulating layer, helping shield the outer bricks from the intense heat inside the smoke chamber. When refractory parging is omitted, heat transfers much more rapidly into the masonry shell, sharply increasing thermal stress between the hot interior and the cooler exterior bricks. When the smoke chamber heats during use, the interior masonry expands significantly. Meanwhile, the outer face of the chimney, especially on an exterior chimney or a buck chimney, remains cold. When the wall is a full 8 inches thick and properly parged, this temperature difference is moderated. But when the wall is only 4 inches thick and unparged, the thermal gradient becomes extreme. The inner portion expands while the outer portion remains almost stationary. Over thousands of heating and cooling cycles, this uneven movement forces a vertical crack to open on the exterior surface of the chimney along the outer face of the smoke chamber. If the crack were caused by settlement, the mortar joints would not remain level. They would slope, separate, or show displacement. The fact that the joints remain perfectly straight confirms that the problem is internal thermal expansion, not structural downward movement. In summary, vertical cracks on the outside of a smoke chamber, when mortar joints are level, are not signs of foundation failure. They are clear evidence of thermal expansion stress caused by walls built too thin and surfaces that were not parged smooth with refractory mortar as required by code. Correcting this issue involves proper parging, restoring the required wall thickness, and ensuring the chimney is rebuilt or repaired to meet IRCR 1001.8 so that heat is safely contained and thermal stresses are minimized. Cleanout openings are an important and often overlooked part of a properly functioning masonry chimney system. They serve two primary purposes. First, as an access point for removing soot, ash, and debris from the base of the chimney. And second, as service and maintenance access for certain fuel-burning appliances that connect into the chimney. Because this area plays both a safety role and a maintenance role, several codes regulate its construction, materials, location, and clearances. For appliances, the International Residential Code R 1003-17 requires that a clean-out opening be provided within 6 inches of the base of the flue. This ensures that debris and soot that fall to the bottom of the chimney can be safely removed without having to dismantle or access the appliance connection. In a masonry chimney where the ash dump door is used as the cleanout, the code requires that the cleanout door be made of ferrous metal or stainless steel and that it remain tightly closed when not in use. This prevents air leakage that could disrupt draft, stops sparks or embers from escaping, and keeps pests or moisture from entering through the opening. Clearances around cleanout doors are critical for fire safety. NFPA 211 Section 7.14 establishes strict limitations on combustible materials near the cleanout access. No combustible material may be located within 18 inches of the cleanout opening. This requirement exists because when the cleanout door is open, residual heat, embers, or sparks can escape, and the surrounding masonry can become quite warm during operation. Ensuring an 18-inch buffer zone prevents accidental ignition of nearby wooden framing, siding, or flooring. NFP 211 also requires that cleanout openings be positioned at least 16 inches above grade. This prevents soil, mulch, or standing water from obstructing the cleanout door and ensures that the opening does not become buried over time. A cleanout below grade would rapidly corrode, clog, or allow groundwater intrusion into the chimney system, which can create severe moisture problems, freezing damage, or draft obstruction. Proper construction of a chimney cleanout is essential not only for building code compliance, but also for long-term safety and serviceability. A well-designed, accessible, and code-compliant cleanout allows chimneys and appliances to be maintained efficiently, prevents moisture and pests from entering, protects combustibles from heat, and ensures the system functions as intended throughout its lifespan. An interior fireplace inspection always begins with one essential step: measuring the fireplace opening. The width and height of the firebox opening determine how large the chimney flue must be in order to draft properly. Every fireplace is designed as a system, and the flue must be proportionally sized to the fireplace opening to ensure adequate draft, smoke removal, and safe operation. Without this measurement, it is impossible to know whether the existing chimney liner is correctly matched to the fireplace. Once the width and height of the fireplace opening are taken, those values are multiplied to determine the fireplace opening area. This number becomes the basis for calculating the required cross-sectional area of the chimney liner. The IRC and NFPA standards provide ratios for sizing the flue relative to the opening, and these ratios vary depending on the shape of the liner. For a round flue liner, the cross-sectional area of the liner should be at least 1/12 of the fireplace opening area. Round liners draft very efficiently because they have no corners, so the system allows a smaller cross-section to serve the same fireplace size. For square or rectangular flue liners, the required ratio increases to 1/10 of the fireplace opening area because corners create turbulence and reduce draft efficiency compared to round liners. If the rectangular liner has an aspect ratio greater than 2, one meaning it is long and narrow, the draft efficiency decreases even further. For these elongated rectangular liners, the required ratio becomes 1/8 of the fireplace opening area, which is sometimes remembered as half again larger compared to a normal rectangular liner. In other words, when a flue is too narrow relative to its height, its ability to carry smoke is reduced, so the code compensates by requiring a larger total cross-sectional area. These ratios are crucial during inspection because many older chimneys were not sized correctly. A mismatched flue can cause smoking problems, poor draft, excessive creosote formation, and overheating. In practice, our preferred flue liner sizes are 13x13 and 13x18 because these liners offer adequate cross-section for most standard residential fireplaces and match the 1/10 sizing rule in the majority of installations. These dimensions also integrate well with typical clay tile systems and allow for proper chimney caps and crown construction according to ASTM C 1283. Measuring the fireplace opening, calculating the area, and comparing it to the liner's cross-section is one of the most important steps in evaluating a fireplace. It immediately reveals whether the system is properly engineered or whether the flue is undersized or oversized, both of which can seriously impact safety and performance. Another critical part of an interior fireplace inspection is measuring the depth of the firebox. This measurement is taken from the joint between the inner hearth and the outer hearth to the back wall of the firebox. The firebox depth must be at least 20 inches. This minimum depth ensures that the fire is positioned far enough back to prevent smoke from rolling forward and spilling into the room. A shallow firebox places the flames and heat too close to the fireplace opening, which disrupts the natural draft pattern and increases the likelihood of smoke escaping into the living space.